All right, so I think this is recording. Let's take a look at Skill Packet 6. We'll do A, B, C, D in different videos. Definition of imaginary unit and complex numbers. I believe that you guys have seen imaginary numbers before, and that maybe this is just going to be a refresher. I've never had a history of math class before, but I believe the mathematician that is credited with doing the most work in solving polynomial equations would be Gauss, a German mathematician that I believe lived in the 1700s, and you can check that out on Wikipedia. One of the most famous mathematicians and best mathematicians in history. Um, so he was very interested in having a complete solutions to any polynomial equation. And I believe when when they studied that x squared plus 1 is equal to 0, he wanted to be able to solve this. And of course, when you try to get x by itself here, we run into a problem within the set of real numbers that there is no real number that when multiplied by itself gives you a negative value, because we know from experience that a positive number times a positive number is positive, and that a negative number times a negative number is also positive, and that 0 times 0 is 0. So what they came up with is said, well, we're going to define a number that we refer to as an imaginary unit that has this property that I squared is equal to negative 1. And then now some textbooks will define the imaginary unit to have this property that I squared is equal to negative 1, and others will say that I is equal to the square root of negative 1. And I'm not, to tell you the truth, I don't understand that sometimes all the technicality and the fights over definitions, that you've got one mathematician that says that this is the definition of an imaginary unit, and another one that says this is the definition, and they fight and argue over which is the true. We're not getting that detailed. Either one of these will serve us fine. So this imaginary unit, with I squared equals negative 1, or to think of it as I is equal to the square root of negative 1, is going to do us fine. Now, we want this to be like any number, as far as we want to be able to add, multiply, subtract, divide this imaginary unit. We want to be able to treat it like any other number. And now it does have that. I guess it's wrong to say any other number, because it does have that property that's unlike any other real numbers. But we want it to have the normal operations. We don't. Um, so one of the things that we're interested in right off the bat with multiplication is different powers of I, and we know properties of exponents as it applied to real numbers, and we're going to still keep that definition that any non-zero base raised to the 0 power is equal to 1, and I to the first power is just I, and I squared by definition was negative 1. Now when we look at I to the third power, why not just use the previous answers and look at it as I squared times I? Because we know with properties of exponents, when the bases are the same, you simply add the exponents. Well, we know that I squared by definition is negative 1, and that negative 1 times I is going to give us a negative I. I to the fourth, let's do that same thing. Let's use this answer above it, the I to the third, times I, because 3 plus 1 is 4. We've just illustrated that I to the third power is negative I, times a positive I is a negative I squared. I squared is negative 1, so this is saying what's the opposite of negative 1, which is positive 1. Then I to the fifth, I to the fourth times I. We just did that I to the fourth was equal to 1, and 1 times I is equal to I. So now I to the sixth can be thought of as I to the fifth power times I, because remember that I is to the first power and 5 plus 1 is 6. We just illustrated that I raised to the fifth power is I, and I times I is I squared, and the I squared by definition is negative 1. I to the 7th can be thought of as I to the 6th times I, and I to the 6th, we just looked at it as illustrated it was -1 times I, negative I. Well, we could continue doing this forever and stuff. Well, is there anything that we recognize? And hopefully you do. And the notes do not list the I just vertically like this. They list it in groups of 4. So what we've seen is that we've got I to the 0 was 1, I to the first power is I squared was -1, and I cubed was negative I. And that pattern repeats. In mathematics, when you see this, they typically refer to it as a cyclic. I don't think I spelled cyclic. Remember, I'm a mathematician, not I can't spell very well. A cyclic pattern, a cycle, and this cycle has a length of 4. You might come up across some other problems someday that have a cycle of a shorter or longer length. So this I to the 4th, we just illustrated that was equal to 1, and that this was equal to I and -1 and negative I, and that continues. So now you have another cycle of 4. And one of the things that I noticed also in learning this was that when you have an even exponent, your answer is always going to either be 1 or -1. And when you have an odd exponent on I, it's going to be either I or negative I. And that's going to serve as a nice check when we really start looking at powers of I that are a lot larger than 15. So let's take a look at one of those right now that's moderately large. Let's look at something like I to the 35th power. Well, I don't think any of us wants to sit here and count out the cycles of 4 to go 15 and then to go 19 and then to go 23 all the way up to 35. You don't want to write that out all the time. You want some way to figure that out. And because it is a cycle of length 4, what we can do is divide this number by 4, the exponent, and look at the remainder. So when we take 35 divided by 4, if 8 times 4 is 32, and this has a remainder of 3. So this I to the 35th can be thought of as I to the 3rd power. Now we do need to know these first 4. We do need to know that this is 1, that this is I, that this is -1, and that this is negative I, and we have our answer. Okay, and if we do this division, even myself, when the numbers start to get large, I'm the worst probably in the class at mental arithmetic. So I'll jump to a calculator pretty quickly. And I'll take that exponent and I'll divide it by 4. So when you think about division, when you think about this remainder, the possibilities of a remainder when you're dividing by 4, if you have a 0 remainder, then that means that value may have been like 36 or 32 where it's divisible by 4. If you have a remainder of 1 or a remainder of 2 or a remainder of 3, or the other possibilities, you're never going to have a remainder of 4 or larger, because that just means that you've made a mistake, that you didn't pick a quotient that was large enough to go into that dividend, that you needed to make your quotient larger. So the only possible remainders when you divide by 4 is 0, 1, 2, or 3. If you divide by n, then it's 0, 1, all the way up to n minus 1 are the possible remainders, right? So when on the calculator, when I see a remainder of 0, something like 32 divided by 0, the decimal representation of that, if I have it on float, but say I have my calculator fixed on a certain decimal and I divide by 4, you can see that the decimal number here, the number following the decimal point is going to be 0. So a lot of students will think of that remainder of 0 as 0.0 if they're using a calculator, and when the remainder is 0, this I to that power is going to be 1. When you have a remainder of 2, you're going to see 0.5 as the number. You're going to see 5 following the decimal point on the calculator when you divide by 4, and a remainder of 2 is I squared, and I squared is negative 1. When you have a remainder of 1, the number that's following the decimal point is going to be 2.5 because you've got 1/4, and 1/4 is 0.25, and that's going to be I to the first is just going to be I. And when you have a remainder of 3/4, you're going to see it after the decimal point a 7.5, and I to the third power is negative 1. So anyway, it'll become more clear. It's pretty early in the morning, and I don't even think I'm thinking straight, but it'll become real clear when we jump in and do some more examples like the I to the 35th that are in the notes. Alright, so I've got I to the 22nd power. That's an even number. I'm expecting to get an answer of either 1 or negative 1. If I pull up a calculator and take 22 divided by 4, I have a remainder of 0.5, a remainder of 2, remainder of 2. So I know that with a remainder of 2, the I to the 22 is the same as I squared, which is equal to negative 1. When I have 81 divided by 4, 0.25, that's a remainder of 1, because that's 1/4. The numerator is the remainder of 1, and I to the first power is just I. Now the numbers are getting larger. 140 divided by 4. I've got that 140 is divisible by 4. So I've got I to the 0 power, which is just 1. 49 divided by 4. With a decimal point of 0.25, that has a remainder of 1 because, 0.25 is 1/4. So with a remainder of 1, I have the I to the 49th power is equal to I. 390 divided by 4. With a decimal of 0.5, that's 2/4. The remainder is 2, that's I squared, but I squared is negative 1. And again, I knew that when I saw an even exponent, I was either going to get a positive 1 or negative 1. I know that when I saw that odd exponent, I was either going to get positive I or negative I. And here, even exponent, either 1 or negative 1. So I forgot to mention that I can have those checks. Alright, so that gives you a little bit of an idea of multiplication of this imaginary unit and how to simplify the powers of I to one of those 4 values. Now we're going to look at and try to recall simplifying radicals. And one thing that we can do with radicals when we have multiplication is split up this square root of a product, a times b, into the square root of a and the square root of b. I believe there's a restriction that both of those can't be negative values. We can look at that, or I can return to that and double check on that property. So when I see the square root of negative 25, I'm immediately going to break it up into the square root of negative 1 times the square root of 25. Because I know that we have that I is equal to the square root of negative 1, so I know that's an I, and the square root of 25, since 25 is a perfect square, why, it's just multiplied by 5, and we typically write it as 5i, just like we do with variables and putting a coefficient. Although this is a number, this is not a variable, but we've seen that style of writing, that style of presenting our answer like that before. Alright, so let's look at another example. So here we have the square root of negative 63. So again, when I see the negative sign, I'm going to treat that as the square root of negative 1, which is I. And I'm going to look at 63, and I'm going to break down 63 to see if I can find the largest perfect square that divides 63, which I believe is 9. I think that 9 times 7 is 63. So when I have the square root of negative 1, times the square root of 9 times the square root of 7, why I can simplify two of these. The square root of negative 1, I can treat that as I. The square root of 9, I can treat that as 3. And the square root of 7, I really can't simplify that any value. That's what they mean with exact values. They do not want me to give a decimal representation of the square root of 7. Now, when they're writing their answers in a textbook, when they're typing it, it's pretty easy to read the typed word in a textbook, and you'll see it typed as 3 times the square root of 7 times an I. Well, in my handwritten notes, sometimes I'm sloppy, and I don't want to have this radical line go too far and accidentally, make people think that I is part of the radicand that's underneath that radical. So what I often do, and what I've seen other teachers and professors and stuff do, is to write this as 3 times I times the square root of 7 and stuff. So that's probably a pretty good habit to get into, just so that you can read your own notes and stuff, especially if your handwriting is questionable, and if somebody else is going to be looking at your work, or if you yourself later on is looking back at your work and you don't want to treat that as the square root of 7i. Let's take a look at here at this one. Same direction, same idea. We see the negative sign, square root of negative 1. We have the square root of 125, and we break that down, and we see that 25 times 5, the biggest perfect square that divides 125, is 25, and you may have to play around with that on a calculator. So we've got the square root of negative 1 times the square root of 25 times the square root of 5, because we can break up that multiplication that's underneath that single radical as the product of these radicals. So that's going to give me an I times 5 times the square root of 5, and I like to present my answer as 5I radical 5. That's just out of habit. Alright. Well, I think that's it for skill part A. I'll do B, C, and D in another video, so I hope this helps, and I'll talk to you later.